Hi everyone, I'm Ryan, and I'll be providing you with an overview about my FYP, Deep Learning for Defect Detection with Super Resolution. This is the agenda for our presentation. I'll introduce you to this topic about super resolution, and we'll discuss about our implemented methods and obtained results. Let's begin with a quick introduction. High-resolution images are desirable in many fields due to containing more detail and higher clarity. In the case for defect detection in semiconductors, these high-resolution images enable defects to be detected more reliably due to having more detail. However, it can be difficult to procure high-resolution images either due to cost or time constraints. Image super-resolution aims to solve this by reconstructing low-resolution images into high-resolution ones. We can assess the quality of these reconstructed images by using image quality metrics such as PSNR and SSIM. In recent times, there has been great improvement in the quality produced by super resolution methods, namely deep learning based methods using residual learning techniques. Therefore, for this project, we aim to determine if deep learning super resolution methods were indeed beneficial to the field of semiconductor defect detection. Additionally, as we are working alongside a semiconductor inspection solutions company, we aim to develop a solution that will enable them to make use of such super resolution technologies. During the span of this project, we implemented three deep learning-based super-resolution methods with reference to the method's respective papers. Firstly, we have SRCNN, which is the classical method of deep learning super-resolution. We use this method as a baseline to benchmark our other methods against. Secondly, we have EDSR, a state-of-the-art super-resolution method that uses residual learning techniques and is among the top scorers in comprehensive reviews of super-resolution methods. Thirdly, we have SRGAN, a super resolution method that takes a different approach to image quality, where instead of learning to minimize pixel-wise differences, this method makes use of the GAN fine-tuning approach to learn the textures of images to improve perceptual quality. As for the testing of methods in this project, we trained our implemented methods on the publicly available diff2k dataset with their respective training configurations from the research papers, and tested these methods using publicly available test datasets that are commonly used in super resolution research, such as the SET5 or SET14 dataset, as well as the company provided datasets. We assessed our implemented methods using the two image quality metrics SSIM and PSNR to obtain a well-rounded overview of the similarity between the upscaled images against the ground truth high-resolution images. Before I go into the results, let me tell you about some experiments that we performed during this project. During our early testing, we observed that the method SR-GAN performed worse than bicubic upsampling of the low-resolution images. However, it produced better texture details, resulting in better perceptual quality. But as these textures differed from the ground truth high-resolution image, SR-GAN ended up scoring even worse than bicubic interpolation. Thus, we aim to improve the performance of SRGAN by performing some experiments. Our first experiment was about changing the VGG model within SRGAN from VGG54 to VGG22, which would decrease the amount of textures being added to the reconstructed images. Our second experiment was to tweak the perceptual loss function used during the GAN fine-tuning step of SRGAN, encouraging the model to learn textures that are more similar to the ground truth high-resolution image. Concluding our experiments, we noted that we managed to greatly improve SRGAN's performance compared to the original implementation, which brings us to our next part. Now let me introduce to you our new method, EDSR-GAN. This method is created by combining the state-of-the-art EDSR method with our improved GAN fine-tuning approach of SR-GAN to produce a model that features both state-of-the-art performance while being able to produce images with more texture detail. To create this model, we first train an EDSR model with its original training configuration. Next, by applying our improved fine-tuning approach that uses VGG22 and our new perceptual loss formulation, we fine-tune our pre-trained EDSR model to learn to produce outputs with better texture quality. After our training, we perform testing on publicly available test datasets, which can be seen from this table, where our new method managed to outperform EDSR in 3 out of 4 of our tests in terms of image quality metrics. Now let me show you some results from our testing, featuring some zoomed-in shots on some of our test images. Here we can observe the various super resolution methods in action. Do notice that super resolution managed to improve the sharpness more than the bicubic upsampling of the low resolution image. From our examples, we know that EDSR and our method EDSR-GAN are among the top performers. We observe that our method EDSR-GAN managed to add more texture detail that is highly similar to the original high-resolution image. Now let me show you some of our test results on the company's images. For our tests on the company datasets, we focus our tests on our method EDSR-GAN, where we would train one version of it on the publicly available diff2k dataset and another version on the company's dataset. Here we can see our results on the company's images. In our testing on company data, we noted that super resolution was able to enhance the quality of images by denoising these images and improving the sharpness of edges. In order to enable our users to make use of super resolution technologies, we created this web application with Gradio. Using the web user interface, users can downscale high-resolution images to prepare low-resolution datasets. Use these datasets to train super-resolution models, and finally perform super-resolution on single images or on a batch of images. Additionally, the web user interface acts as a unified platform to train and evaluate the super-resolution methods on image quality metrics. Concluding this overview of our project, firstly, we implemented various methods of deep learning super resolution. Secondly, we developed an interface that facilitates using super resolution technologies without interacting with code. Thirdly, we improved upon existing methods to create a new method of super resolution, EDSR again. And lastly, we verified that super resolution does indeed benefit defect detection, as it is capable of producing higher quality images with reduced noise and sharpened edges as compared to the upsampling of low resolution images.